Good morning, everyone. My name is David Fucik, and I'm happy to present to you our work called STALP, Style Transfer with Auxiliary Limited Pairing. This work was developed as a collaboration between our university and the great people at Adobe. To jump right in, let us suppose that we create a sequence of video frames like we see on screen here. This will typically be a pre-recorded sequence, often with a static camera position. It can be recorded in a controlled environment, like here with a green screen background, but that is not a requirement. Once we have our sequence, we ask an artist to paint over one or multiple selected keyframes, which we call pairs. They can choose whatever medium or color palette they wish, though the most appealing scenarios arise when physical media such as oil paint or watercolor is used. Our goal is to then turn their creation into a living painting by applying the style consistently over the entire sequence. Several methods to accomplish this task have been proposed. One of such methods is the one by Jamriška et al. Published at SIGGRAPH 2019. This is a non-parametric patch-based method, building on the foundation of image analogies. To keep the result consistent between frames, it uses Optical Flow estimation algorithm to guide the synthesis. When used correctly, it produces high-quality results, which are very faithful to the original style exemplar and remain temporally coherent. However, it has several downsides which prove to be difficult to address using this approach. Because optical flow is used, it requires small delta between each two consecutive frames, starting from the paired keyframe and working sequentially, where the next frame cannot be synthesized before the previous result is known. This mode of operation limits some potential use cases. Furthermore, the synthesized result stays reasonable only when the content in the scene does not change considerably. In practice, this typically holds only for a few dozen frames. The artist needs to create more keyframes to ensure the synthesis stays reasonable over more frames, and synthesis results produced from multiple keyframes need to be merged explicitly. On the other hand, using machine learning seems to be an obvious candidate for this task. However, we are faced with the problem of having a very limited dataset at our disposal, often effectively just one pair on which we can train a model. For a classical image translation task, this is a fundamental problem, since the model will strongly overfit on the one example that we train on. And so, Texler et al. Attempt to sidestep this issue by limiting the scope of what the network can see during training, by feeding it small batches of image patches cut out from the training example. Because their architecture is fully convolutional, at test time they can produce full images in a single feed-forward pass. This produces interesting results and has many advantages. First, it shows a preview of the results in seconds or minutes, making it highly interactive and fun for users to utilize as a creative tool. Second, because you don't need the previous synthesized frame, it can be applied to any frame or in parallel. That opens up use cases where there isn't necessarily full continuity between frames. Lastly, because you can sample patches from multiple keyframes without restriction, the translation network learns to create an implicit merging of content and no explicit blending is required. Unfortunately, it has some significant downsides. Because there is no temporal link during training, it tends to be sensitive to various changes in the scene, such as extreme poses or slight changes in lighting conditions, which results in temporal flicker. To make the method temporally coherent, it offers a special mode by generating additional guidance. However, that requires the approach to do additional pre-processing of the input video beforehand. To address the issues of previous methods, we propose our new method. To recap, we have our video sequence consisting of individual frames, in this case, a gesturing child. We ask an artist to paint us a stylized version of the first frame, thus creating our paired keyframe. Like Texler et al., we train an image translation network to synthesize the rest of the sequence, all the while minimizing the L1 loss per pixel function on the original keyframe to ensure that the style on this artist-prepared frame is preserved as closely as possible. A key difference in our approach is that we don't train the image translation network on small patches. Instead, we use full images, and to prevent overfitting onto the keyframe, we use a different strategy. Since the keyframe pair is not the only data we have available at train time, in fact, in most cases we have the entire sequence or at least a few other unstylized frames available, we use such additional information during the training process. Although we don't know the stylized counterparts for those other frames, we expect that the stylization should be consistent with the keyframe. Therefore, we employ a style loss between the stylized image our artist created and what our network predicts for non-keyframe inputs. The purpose of this loss is twofold. One, to ensure that the frames of the given sequence have consistent stylization, and two, to prevent overfitting on single keyframe. However, measuring distance between styles of two images is a notoriously hard problem. Several empirical metrics based on responses of existing neural networks have been proposed by previous work, in particular to perform general style transfer. One such metric was proposed by Leon Gattis and his collaborators from 2016 paper Image Style Transfer using Convolutional Neural Networks. And it works by first extracting various deep features computed using the VGG classification network. Then we compute gram matrices of these features, where each element is the unnormalized cross-correlation between two channels of the extracted features. Perhaps slightly surprisingly, this matrix is a relatively good representation of style. For example, these two images have very similar VGG gram matrices as the input image. Even though Gattis et al. Use this metric to perform style transfer through backpropagation, it can be used to train a conventional feed-forward network. That is exactly what Johnson et al. Did in 2016 in their perceptual losses for real-time style transfer and super resolution. They train a network for stylization such that the gram matrices of the result and the style image are similar, while enforcing that the VGG features of the result and input content image remain the same. So why don't we just use methods of neural style transfer to stylize our sequence? Well, the first problem is that using the gram matrix loss as the only way to transfer style results in transfer that does not follow semantics of the images very well. For example, in this case we can see that while the result has roughly correct color palette and low-level features, it looks more like a mishmash made from the style exemplar. The eyes are not projected onto the target eyes, for example. In short, the transfer is not semantically aware. The other problem we can see here is that the resulting style is of much lower quality compared to what it looked like in the style exemplar, and this problem is partly caused by the explicit content loss used by Gattis and Johnson. To get back to our method, the style consistency metric we use is the gram matrix loss too, very much like Johnson and Gattis. However, note that except for the given keyframe pair, we have no explicit content loss between our frames and their stylization, which is unlike Johnson's method. A natural question here is why would the content be preserved at all if there is no content loss? Well, we conjecture the reason is because the gram matrix loss is relatively weak metric of style and because it would be more difficult to learn to reproduce the style exemplar regardless of input than to perform some kind of translation. Our keyframe L1 loss also works as a regularizer here. Thanks to the L1 loss, we also introduced semantic mapping as explicitly created by the artist who gave us the pair. For further technical details, we use the existing architecture shared by Fuchik et al. 2019 and Texler et al. 2020. This is an encoder-decoder architecture with skip connections and residual blocks in the middle. The downsampling is done in a typical strided convolution way, and the upsampling is implemented as nearest neighbor upsampling followed by a learned convolutional kernel. This architecture has proven itself to be very useful for stylization tasks, mainly because the intermediate representations only downsample the input to 1/4 resolution, which allows it to retain relatively high levels of detail and tends not to suffer from deconvolution artifacts. Our training schedule works by computing the L1 loss on our paired keyframe. Then we randomly select one frame from the rest of the sequence, running it through the network, then computing the gram matrix style loss between the style exemplar and this predicted frame. Then we sum up the gradients from these two loss functions and perform an optimization step on the network. Unlike in Gattis or Johnson, where only 4 layers of gram matrices contribute to the total style loss metric, we found it beneficial for the style quality to compute them over all layers of the VGG network. Since the two loss functions are not scaled, we use a constant scaling parameter. Note that this is sufficient because gram matrix loss only depends on the number of dimensions of VGG features and not the size of the input. Additionally, some notes about the properties of our setup. The set of frames out of which we sample to compute the style consistency loss does not need to contain the entire sequence. That is, a carefully selected subset is often sufficient and sometimes even beneficial compared to the full sequence. Lastly, once our network is trained, the inference can run in real time. And finally, we can demonstrate some results. In this sequence, we can observe that our method indeed faithfully preserves the style exemplar throughout the entire sequence. Especially note how the details on hair and face remain crisp. Furthermore, the sequence produced by our method is temporally stable with minimal flickering. This is the byproduct of computing the style loss evenly over all frames in the sequence. The quality of results produced by our approach is best appreciated in comparison to previous methods. Here we see another sequence compared to Jamriška and Texler. The first thing we can notice is that Jamriška produces significant washed out look as the sequence moves further from the keyframe. To a lesser extent, this is also true for Texler. Note the missing details on the arms. Our method retains even smaller details for the full length of the sequence. The difference is most observable on the shirt and the arms. In this sequence, we can see how methods of Jamriška and Texler created blurred effects as the sequence moves away from the keyframe, which ends up looking more like a smeared photograph. Our method, on the other hand, does not blur out the style and synthesizes images which manage to show features similar to those painted in the style exemplar. Also note the flickering in Texler's method when the temporal coherence is not explicitly treated, whereas our method manages to be consistent by default. When we compare the three methods using the most extreme pose images, the blurring effect produced by other methods is clearly visible. As a slightly different use case, we can apply our method to 3D model stylization by creating a sample rendering and stylizing it as a video sequence. This is different from texture mapping because the stylization retains the planarity of the original style exemplar. One of the big emergent advantages of our method is that thanks to being less sensitive to changes in the scene than Texler, it can be applied even in situations where the input is not necessarily a video sequence. For example, we can replace it with a set of photographs that were taken under similar conditions. We successfully applied our methods to two such scenarios, first of which being face stylization of portraits taken under the same lighting conditions and with the same background. Just like before, we ask an artist to create a paired keyframe. However, this time we don't have a video sequence to stylize, but a few unpaired images from the same underlying distribution. Our method is able to perform style transfer even in this case. In a sense, we can look at the provided keyframe pair as giving us a template of how to transfer style from our input domain. These results show that we can transfer detailed structures and remain semantically correct while doing so. Here is a comparison of the setup with Johnson's method. As you can see, the explicit content loss in Johnson causes great loss of detail in style features, which results in a filter-like appearance of the result. The other scenario that we devise is a panorama autopainting scenario. Assume we acquired a set of images which compose into cylindrical panorama. Then we ask an artist to stylize one of these images, and our goal is to consistently stylize the entire panorama. And here we see the result. While the style of the results retains planarity of the exemplar, it also looks natural when the panorama is stitched together. And here is the result compared to the state-of-the-art general neural style transfer method. Notice that while it mostly manages to produce semantically meaningful transfer, the overall quality of stylization suffers, whereas our result stays very truthful to the style exemplar. Lastly, because we do not require the entire sequence be known during training, we can train a model on a few frames and, assuming the conditions stay comparable, use it for live stylization transfer scenarios, such as a Zoom or a Skype call. Again, compared to Textler, we managed to stay temporally coherent and retain more detail from the style exemplar over changes in the sequence. To sum up, compared to Jamriška and Textler, generally our method is able to resist falling apart longer as the sequence moves away from the keyframe. This is a graph of an empirical typical case of video stylization. While Jamriška produces top-notch quality, the synthesis fails relatively quickly. While Textler can resist a little longer, generally the two methods require a similar number of artist-created keyframes to stylize the entire sequence. That is in contrast to our method, which resists even significant changes in the scene and thus requires fewer provided keyframes, reducing the amount of work that needs to be done by an artist. Finally, we can look at the comparison of the runtimes of our compared methods. All of these times refer to running time on a single V100 NVIDIA GPU. While Jamriška doesn't require any pre-training, each frame takes roughly 5 seconds to synthesize. Textler et al. Trained their network in several minutes, typically taking at least 10 to 15 minutes to obtain a reasonable result. And running inference takes about 80 milliseconds, which translates to about 12 FPS on this kind of GPU. Because the gram matrix style loss is slow to converge, our training schedule takes up to several hours to converge. However, once the model is trained, the inference runs exactly as fast as Textler's due to shared use of the same neural network architecture. As always, there are some limitations to our method. One big limitation is the just mentioned fact that it takes on the order of hours to train a model. This means users are less able and less likely to experiment with the system. Another limitation is something you may have noticed in the results, and whether it's a feature or a bug depends entirely on your use case. Our method sometimes acts much like the patch-based synthesis, where the content of the result is copy-pasted from the style exemplar. Here we can see the eye is still facing forward, even though the head has rotated to a different position. This seems to mostly happen with prominent features such as eyes. Other usual limitations, of course, still apply. Like previously, keyframe selection, that is, which frame the artist should paint over, remains an open problem. In summary, we presented a novel method for stylization with limited style pairing, which significantly improves state-of-the-art in keyframe video stylization. Some of the lessons we learned include: less is more. Explicit content loss, like Johnson's et al., decreases the overall style quality and makes it difficult to retain detail throughout sequences. Style preservation and content preservation is of course a trade-off that needs to be considered, and it's difficult to deal with automatically. And therefore, making use of features extracted from neural networks can be of great benefit to video stylization. And that is it for our paper. Thank you very much for attending our session and taking the time to see our work.